Hello again, my curious engineer. In the previous lesson, you discovered what a microcontroller does. It senses the physical world, processes information, and creates a response. Now we can move closer, not into every transistor, not into every page of the datasheet, only close enough to let the hidden structure begin to open for you. Our guide will be the Amiga 328P, a classic 8-bit AVR microcontroller used on the Arduino Uno R3 and on many traditional nano boards. For a moment, simply look at it. A small black package, 28 metal legs, no screen, no keyboard. Almost nothing outside reveals how much is waiting within. And while you notice that contrast, small outside, quietly crowded inside, let your attention rest between what is visible and what is still concealed. Inside are a processor, several kinds of memory, input and output circuitry, timers, communication hardware, an analog to digital converter, interrupt logic, and other systems waiting for firmware to give them direction. We are using one real device so the general idea becomes tangible, close enough to examine, intimate enough to remember. By the end, the pinout and block diagram should no longer feel like cold walls of symbols. They will begin to feel like maps, and you may enjoy the moment when the map starts quietly inviting you in. Begin with the pins, the small metal contacts around the package. They are the points where the silicon inside meets the circuit outside. Power enters through some. Ground completes the path through others. One can reset the device. Two may connect to an external clock source. Many others can receive signals, send signals, or do both. A pin used to receive information is an input. A pin used to control something outside is an output. Some inputs understand only two digital states, low or high, 0 or 1. Other pins can measure a changing voltage through the analog to digital converter and turn it into a number. But a physical pin does not always have only one identity. One pin may behave as a simple input or output. Then, when firmware configures it differently, become part of a timer, a serial interface, an interrupt input, or an analog measurement channel. This is pin multiplexing. One tiny contact, several possible rules, one point of connection waiting for the program to decide how it will be used. That is why a pinout looks crowded. A label such as PB5 may appear beside SCK and PCINT5. These are not separate pins, but several functions sharing one physical connection. There is no need to memorize them now. Just notice the pattern. A limited number of contacts, many hidden possibilities, and a program that selects which possibility becomes real. At the center is the AVR CPU core. The Amiga 328P is called an 8-bit microcontroller because its processor performs many basic operations on 8-bit pieces of data. 8 bits form 256 possible patterns. Larger values are possible. They require several operations. Close to the core are 32 working registers. They hold values the CPU needs immediately, keeping them near, available, ready to change without reaching into larger memory for every step. The processor follows instructions stored in program memory. Load, compare, add, subtract, shift, branch, read a peripheral, write to a pin. One instruction follows another, guided by the clock. The clock is the pulse of the chip, a repeated electrical rhythm giving internal operations their timing. Imagine it as a soft, relentless beat beneath everything else, almost hidden, yet shaping every movement within. The Amiga 328P can use different clock sources and frequencies. The familiar 16 MHz belongs to the standard Arduino Uno configuration. It is not an inseparable property of the chip. 16 million pulses each second. And while that number settles, notice the contrast. So much activity inside, so little movement outside. A quiet surface, holding a disciplined rhythm beneath it. Tension gathered into timing, then released as one precise action after another. The Amiga 328P contains 3 important kinds of memory. Flash stores the firmware, the compiled instructions the CPU will execute. It provides 32 kilobytes of flash. Its contents remain when power is removed, so the program is there, waiting when the device wakes again. SRAM is the working space. The Amiga 328P has 2 kilobytes of SRAM for variables, temporary values, buffers, and the program stack. The stack supports function calls, local data, and the path back to earlier code. SRAM is fast and responsive, holding what is needed now, then letting it go when power disappears. EEPROM is different. Its 1 kilobyte can preserve data without power, settings, calibration values, counters, or another state the device should remember after restarting. Keep the roles separate. Flash holds the program, SRAM holds the present work, EEPROM holds what should remain. These roles may become easier to remember when each has its own sensation, the enduring pattern, the movement of current work, the small protected space that refuses to forget. These capacities may seem tiny beside a modern computer. That closeness is part of embedded programming. Every byte matters. Every choice occupies real space. There is pleasure in that precision, fitting complete behavior inside narrow boundaries, with nothing wasted and every part placed exactly where it belongs. Now return to the pins, but look at them more carefully. The Amiga 328P has general-purpose input and output pins, often shortened to GPIO. General purpose means firmware can usually configure the same line as an input or as an output. The chip groups many of these lines into port B, port C, and port D. A port is simply a small group of related pins controlled together through hardware registers. A name such as PB5 means bit 5 of port B. That same electrical connection can be described at several levels. On the DIP package, PB5 is physical pin 19, microcontroller signal PB5, Arduino pin D13, 1 connection, 3 names, each belonging to a different layer. Some pins also connect to analog measurement channels. On Arduino Uno, the pins called A0 through A5 lead to ADC channels inside the Amiga 328P. They can measure changing voltage, and many of them can also be used as ordinary digital input or output lines. Let that correspondence settle gently, because later, when a simple Arduino number appears in code, you will already sense the deeper structure beneath it. One visible label, one hidden mapping, one exact point where software reaches outward and the physical world answers back. A around the CPU and memory are peripheral systems. These hardware blocks perform useful work without forcing the processor to create each transition manually. Timers count clock pulses. They measure intervals, create periodic events, generate PWM signals, and support timing. The analog to digital converter measures voltage and turns it into a number. In the Atmega 328P, it produces a 10-bit result, 1024 possible levels. USART provides serial communication. SPI and the two-wire interface connect the microcontroller to displays, sensors, memories, and other chips. Interrupt logic can make the CPU temporarily change direction when an important event arrives. The watchdog can notice when software stops behaving as expected and reset the device. There is also an analog comparator and sleep modes. You do not need to master any of this today. For now, allow the distinction to become clear. The CPU executes instructions. The peripherals touch time, voltage, signals, and communication. Firmware brings them together, choosing, configuring, coordinating, until separate mechanisms begin to move as one intentional system. Many small parts, each with its own boundary, each responding at the right moment, and when the program guides them well, the whole chip becomes calm, precise, and exquisitely responsive to the behavior you designed. A microcontroller also needs the right conditions around it. It needs power and ground. It needs a clock source. Internal or external, reset must be held in the proper state. And firmware must be written into flash. Without those conditions, all the hidden capability remains still, present, but unable to become behavior. When power arrives, reset places the CPU at a defined starting point. The processor reads flash, and those instructions configure memory, pins, timers, and communication hardware. Then the device enters the pattern its designer created. Read an input, update a value, wait for an event, change an output, sleep until something needs attention. The rhythm from our previous lesson is still here. Sense, process, respond. But now, as you let your attention move inward, you can see what supports each step. A pin receives the signal. Input circuitry interprets the voltage. A register holds the state. The CPU makes the decision. A peripheral may measure time or handle communication. Another pin carries the response back into the world. The black package has not changed. Only your perception has. One silent object becomes a collection of systems close together, sharing time, memory, and signals. And perhaps that is part of embedded work's attraction, touching one small point, then feeling an entire hidden structure answer beneath it. The Atmega 328P is capable and deliberately limited. Its memory, pins, timers, interfaces, ADC, interrupts, and watchdog are finite. Its pins also have electrical limits. They cannot safely power every load directly. Motors, relays, powerful LEDs, and other demanding devices need suitable driver circuits. Those boundaries are not an inconvenience to hide. They define the space in which a reliable design can exist. An embedded engineer learns to respect voltage, current, memory, timing, and the capabilities of each pin. Respecting a boundary makes control cleaner, safer, and more satisfying. Now you know what it means for a complete control system to exist inside one chip. A core to execute, memory to hold, pins to touch the world, peripherals to measure, count, communicate, and react, firmware to give all of it purpose. Stay with that image for one more moment. The small black package, the hidden rhythm, the precise exchange between signal and response. Then let a question begin to open. If the Mega 328P already contains so much, why place it on a larger board? Why add USB, headers, regulators, LEDs, reset circuitry, and other components around it? Keep that tension of curiosity warm, letting the question remain unfinished. In the next lesson, we will discover what Arduino really is, and what an Arduino board adds around the microcontroller.